We're going to have a look at electron configuration, so electron arrangement as you might have called it at GCSE, and we're going to look at some ionization energy stuff based on that. So this is for AS level. So by now you would have known that you're veering away from this writing electron arrangements of atoms in that 2-8-8 structure that you did at GCSE, and moving towards using the SPD, sometimes called SPDF notation, but SPD as far as we're concerned at AS level. Okay, now I'll just explain what this sequence is here. So this is, whereas at GCSE you might have taken, for example, magnesium, you would have realised there's 12 electrons in it, and you would have written 2, 8, 2 for the electron arrangement. We now have to understand that these electron shells, 1, 2 and 3 electron shells, are actually split up into what we call subshells, and the subshells themselves are made up of orbitals. Now the shells get names, and that they still get called 1, 2, 3, 4, but now they're split into subshells, and we call the subshells S's, P's and D's. There are other F subshells, but they're beyond the context of AS level chemistry. So those are our shells, 1, 2, 3, 4, our quantum levels, and our subshells S, P's and D's. Those subshells themselves then exist as a collection of orbitals. Now S subshells only have one orbital in it, okay, and that is a little S orbital, okay. It is spherical, so it is three-dimensionally that shape, so imagine a ping pong ball, I suppose. Okay, we have p orbitals, which you may also have to know the shape of, which are this dumbbell shaped. Okay, now p orbitals, if you see here, they hold 6 electrons. That's what this number represents here, and that is because they're made up of 3 individual orbitals called px, py and pz, again beyond AS level chemistry, and each orbital holds 2 electrons, so in total the p orbital can hold 6 electrons in 3 dumbbell shaped orbitals. The d subshell contains 5 orbitals, so therefore can contain, each orbital containing 2 electrons can contain a total of 10 electrons. Now we don't need to be able to trace or sketch the shape of a d orbital. Okay, so this then is the numbers that we have here, and these numbers represent how many electrons are in the particular orbitals on subshells. Now, next thing then we need to be able to do is you're going to have to simply memorize this sequence of filling of the orbitals. So they fill from the lowest energy level orbital, which is the 1s2, right up to the 4p6. This is as far as we have to go. In fact, we probably don't even have to go that far. At AS level, it's more likely to be 3d in AS level. So this is something you simply have to commit to memory, and it goes 1s2, 2s2, 2p6, 3s2, 3p6. Then there's a little anomaly where, in actual fact, a 4th energy level orbital or subshell fills before a 3d. Now again, the reasons for that, really they are in that when there are electrons in this, it actually then moves up to a higher energy level, if you like, but it's again beyond AS level chemistry. So when we're filling these, we don't go from 3p to 3d, we go 3p into the 4s orbital, and then we go to the 3d. But when we're emptying them, these are taking electrons back out and turning this into an ion. At that point then, the 4s electron will be up here, or the 4s subshell, will be up here, and we would remove electrons from it prior to removing electrons from the 3d. So that's something to bear in mind, okay, and just be careful of that. So that's sort of the terminology and what's going on in terms of filling and electrons and orbitals. We'll have a look at just writing a few, and hopefully that will allow you to do that, and then we'll look at ionization energy. So we'll just take a few examples from the periodic table, and hopefully maybe you can pause the video and do them yourself using that list of filling of orbitals that I just showed you. So if we take very simply first carbon, okay, which in old money, if you like, is 2, 4, and if we were writing it now, it is 1s2, that's 2 electrons accounted for, 2s2, and then we're into the 2p, and we've 2 electrons left over, so it will be 2p2. And that's our total of 6 electrons accounted for, and you can see why there's 4 in the outer shell, and the outer shell is the second quantum level. Let's take then something a little bit more, with a few more electrons in it, so we'll take calcium, which is 20 electrons. So again, 1s2, 2s2, 2p6, that brings us up to 10 of the 20 electrons. Okay, 3s2, 3p6, and then we're into that filling of the 4s before we get to 3d, and that would be a Spd notation for calcium. And you can see we would normally write calcium as 2, 8, 8, 2, and there are indeed 2 electrons in the outer shell. Okay, and let's look at then maybe going into the transition metals where things get a little bit hairy. So we're up to 23 now. So again, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So that brings us up to, again, to 20. And then from there we would go into our 3D, and we've got 3 left over. Sorry, 3D, 3 of course. Okay, now I just want to bring your attention to a couple of anomalous ones that we just need to be a little bit careful of, and we'll do chromium, and chromium is 24. And if I was to say that chromium should be the same the whole way down, we may then think that chromium should be 4s2, 3d, 4, which is fair enough. But in actual fact, because s orbitals are so small and the electrons that are in them repel each other very, very extensively, whereas in d orbitals they're much more diffuse volumes of space and the electrons don't repel each other to the same extent. One of these electrons, just to get greater stability, will pop itself up into a 3d orbital, and that will give us, let's remove that will give us 4s1, 3d5. So both of these are now what we might refer to as half-filled stability. Okay, and half-filled subshells minimizes repulsions between electrons and gives greater stability, and that's the configuration that chromium would, of course, adopt then, instead of the one that we might predict from the sequence of orbital filling. Right, then we go to, I'll do another anomalous one again, which is copper. Okay, and copper has atomic number of 29. Okay, and again I'll just bring that down because that would be the same, brings us to 20. We then have 9 to deal with, and we might well go 4s2, okay, 3d, 4s2, that's 3d, sorry, so 4s2, 3d9. Okay, so that brings us up to our total of 29. Okay, alright. Now, again, we might think that's reasonable based on what we did earlier. However, we can get a half-filled S here if we turn the 3D into a fully filled subshell. And again, because S's are so small and repulsive forces are so significant between them, putting that into a single electron here and fully filling the 3D, where electrons don't repel each other to the same extent in the orbitals, means that we bring this to a lower energy level, and this is actually the configuration here of a copper atom. Right, we'll have a look then, let me just tidy this up a little second, and then we'll have a look at how we would write electron configurations for ions. So if we do our chromium, 4s1, 3d5. Okay, and (3d10). Now let's say the examiner then said, okay, well let's turn this from a calcium atom here into a calcium 2 plus ion. Well, that's a nice simple one. We simply remove the 2 outer shell electrons, which would be that, and this would then be our answer to a calcium ion. If we were asked for a vanadium, and let's say we were asked for a vanadium 3 plus ion, we would remove the 3 outermost electrons. Remember what I said earlier? When the 4s has electrons in it, it moves up beyond to a higher energy level than the 3d. So we take 2 out there and we change the 3d from 3d3 to 3d1. So the red circled answer would now be the electron configuration of a vanadium 3 plus. Likewise, if I had a chromium, let's say a chromium 2 plus, okay, to take the first electron out to turn it into chromium 1 plus would be that, and we would drop that from a 5 down to a 4. Okay, let's take a copper 2 plus, and again that brings it down to a copper 1 plus, getting rid of the 4s1, and then we go to a 3d9. So that's how we turn the atoms in Spd notation into ions. Now, we're going to look then at these orbitals in a little bit more detail, and we're going to draw some what we call electrons in box notation. So it's the same sort of idea, but we're looking at the electrons in boxes this time, and this splits the subshells up into their individual orbitals. So if it took, let's take magnesium again, okay, and that was 1s2, 2s2, 2p6, 3s2. So we represent each orbital this time as a little box. So remember, I said earlier that the p orbitals have, or the p subshells have 3 orbitals, and the s subshells only have 1. Now we then can be asked to represent the electrons in these, and we have to represent them in opposite pointing arrows, and that's just to represent that the electrons would be spinning in opposite directions. So therefore, for this configuration, we would have as so. So that's nice and simple. Okay, let's take a look then at perhaps something like nitrogen. Okay, and we know that nitrogen is 7, so it's going to be 1s2, 2s2, 2p3. Now, we just need to be a wee bit careful here. The first 2 subshells are very easy. Third one, there's something we just need to have our attention drawn to. So 1s2 is as so, 2s2 is as so. But here, some people may do this, okay, for our 2p3. But remember, the electrons will arrange themselves in such a way as to minimize the repulsions. So in actual fact, rather than that, we should represent nitrogen as so. If we went then through to oxygen, okay, which is 8, so it's just the same, 1s2, 2s2, and then 2p4. So same idea, we do our boxes representing our orbitals. We'll have 2 in there in opposite spins, 2 in there in opposite spins. We'll have our 3 here, and then we have a final one here where we do have 2 electrons into the same orbital. Okay, and that is how oxygen occurs. And that's the same for any. If I had a final electron configuration of 3d5, you would represent those. So remember that these have got 5 orbitals in them, so we need 5 boxes, and it would be a single-headed or a single arrow in each of those boxes. Okay, now, so hopefully that allows you to do your SPDFs, turn your SPDFs from atoms and represent them as ions, and then likewise illustrate those as electrons in box notation. We're going to look now at ionization energy, which gives us evidence for these electrons existing in shells, subshells and orbitals. So if we remind ourselves, first of all, what ionization energy actually is. So it's the energy needed to remove 1 mole of electrons from 1 mole of gaseous atoms. So that's a pretty commonly asked question, and again one of your definitions that you will be expected to know. So if we were to write the arrangement, or sorry, the equation for it, so magnesium, for example, and we must put gas because to remove the electrons from 1 mole of gas, that will go to magnesium, which is still gas, plus an electron has been given off because it's the energy needed to remove 1 mole of electrons from 1 mole, but the magnesium is now +1. Okay, so that's the energy, and you will have a delta H there. Okay, and that will be a positive delta H because it's endothermic, because you need energy to overcome this attraction. Now, what is it that determines how much energy is needed here? Well, obviously you have a nucleus, and in this case you have 12 positives in the nucleus for magnesium, and then you have got your electron configuration, and this is our electron configuration for magnesium. So you have two forces at play here really that control how much energy is needed to remove this electron. Force 1 is an attractive force, an electrostatic attraction, the force between the nucleus and the outer electron. But you also have repulsive forces. So you have these electrons here, okay, which will repel. And it's a balance between the attractive force of the nucleus and the repulsive force of these electrons here, okay, that will actually control how much energy is needed to remove this electron. You also have this electrostatic attraction here, okay, can be weakened or diminished by the number of shells between the outer electron and the nucleus, okay, and that is a thing called shielding. So you're really shielding the nucleus from or shielding the attractive force of the nucleus from the outer electrons. So it's the shielding of the nucleus by the shells, or the quantum levels, the shells, to the outer electron. Okay. So when you're asked in a question, what is it that controls the magnitude of the ionization energy, it is a combination of shells, shielding. Okay, the more shells you also have, the greater the distance. So you might talk about radius. That may in some aspects be atomic, but it might also be ionic. If you're talking about successive ionization energies, we'll come to those in a little while. So you're talking about shells, you're talking about shielding, you're talking about the electrostatic attraction between the nucleus and that outer electron. And if we look at perhaps a couple of examples here, so if I looked at the change in first ionization energy, I went from sodium to potassium. Now sodium is 281, okay, and it has a positive charge in its nucleus of 11 in its nucleus, whereas potassium is 2881 and it has 19 protons in its nucleus. Now, how does the first ionization energy change from here to here? Well, I will tell you that as we go down a group, okay, it will get less. Now, you might say, well, it shouldn't get less because we've got a greater positive charge in the nucleus and potassium, therefore this attraction, this electrostatic attraction, would be greater. However, we have one more shell, so we have a greater amount of shielding. We have a greater atomic, so we'll just say more shielding. We have a greater, in this case it is atomic radius, and therefore we have a greater distance. And that distance is between the nucleus and the outer electron, and that therefore weakens the electrostatic attraction. And that is the reason that we have a reduced first ionization energy as we go down a group. So those are all the sorts of things that you want to get in your answer. So despite the fact that we have greater net nuclear nuclear charge, okay, we have more shells, therefore we have more shielding, and therefore the outer electron has got a weaker electrostatic attraction force between it and the nucleus. Let's have a look then if we maybe went across a period. So if we were going across, perhaps typically the examiner might ask you lithium. If you have your periodic table with you, it would be a good idea, across to fluorine. Now what changes as we go across there? Well, lithium has a 3+ in its nucleus, fluorine has 9 protons in its nucleus, so nuclear charge increases. What about shells and shielding? Well, no, because that starts off at 2,1 and that goes up to, that goes to 2,7. So we have the same shells, and that gives, well, it doesn't give us the same shielding, it gives us very similar shielding. And there are a couple of anomalies to this, and we'll look at those in a little while. Okay, so this time, and therefore that gives us also similar distance, okay, between the nucleus and the outer shelled electron. So as we go across here then, the first ionization energy actually increases, and the dominant factor this time is indeed the positive charge in the nucleus holding that outer shelled electron more rigidly. In actual fact, if we were to draw the size of these as we go across, you will also find that atomic radius would actually decrease as we go from there to there, because you get this +9 pulling these electrons into shells into a smaller volume of space. So the outer electron ends up being closer to the nucleus of the fluorine than it is to the lithium. So if we were to go draw a graph of first ionization energy as we went down a group, okay, against, so if we were to do it for lithium to sodium to potassium, so lithium, sodium, potassium, we would see a decrease in the energy needed to remove the first electron from that. If we were to do it going across a group, okay, so let's say we did it lithium across to fluorine, we would see a general increase in first ionization energy. And again, you'll need to be able to explain that. Then we'll have a look at a couple of little anomalies in that last trend that I looked at. So if I was going across a group, so let's say I was going, across a period, I was going to lithium, to beryllium. There's actually a little dip here to boron, which is against our general trend. So if I just sort of draw in the general trend of first ionization energy across a period, then we would go up again to carbon, and we would go up again to nitrogen, and then we would actually have a little bit of a plateau or maybe a drop to oxygen, and then we would go to fluorine. So you guys need to be able to explain that, and that we will explain the general increase. Okay, now in order to explain the first one, and the same would be true if you were asked for the respective elements down below it. So in other words, instead of going beryllium to boron, they might ask you magnesium to aluminium. Instead of nitrogen to oxygen, they might ask you phosphorus to sulfur. So the same reasoning, except you're in the next quantum level out. So you're going 3 to, instead of here you're quantum level 2, you'll be going quantum level 3 there. So let's do beryllium, and we now need to go to Spd notation to start explaining this. So this is 1s2, 2s2. Boron is 1s2, 2s2, 2p1. So what you'll see here is we're now going from S out into the next subshell, and that tiny little increase in shielding here, okay, offsets the fact that beryllium has got 4 protons in its nucleus, and boron has 5 protons in its nucleus. So this little amount of increase of shielding here, shielding the 2p1 electron from the nucleus of boron, that isn't relevant in beryllium, okay, allows for this little drop off. So in other words, this reduced attraction of the nucleus to the outer shell electron in boron. So that's that, and that would be the same argument for magnesium going to aluminium, except it would be the 3s2 going to the 3p. If we look at this nitrogen to oxygen, we can't explain that in the same way. If we look at the electron configuration of nitrogen, it is 1s2, 2s2, 2p3, oxygen 1s2, 2s2, 2p4. So there's no increase in shielding here. So let's break this down a bit further into, this time, electron in boxes that we looked at earlier. And we do the nitrogen has got 3 electrons, and the oxygen has got 4. And the reason for the reduction in the unexpected or unpredicted reduction in first ionization energy for oxygen is because you now have 2 electrons in one p orbital, and those electrons would of course repel each other. And if there's that little amount of repulsion that we have there, even though there's one more proton in oxygen, that amount of repulsion means that it takes less energy to remove that electron. Over here we have nice, what we might call half-filled stability here. Okay, so there's no repulsion going on between the electrons in nitrogen, whereas we get that in oxygen. The same would be true if you're asked for the next period down, phosphorus through to sulfur. Okay. So we'll have a look now at some what we call successive ionization energies, and that just simply means you keep on removing electrons. So in other words, in this case we had first ionization energy, then if the examiner asked us to write for second, that would be removing a second electron. Okay, so we're still only removing 1 electron, so that is your second ionization energy. They may then ask you for an equation for the third, and again we start from the second, we don't go back to start a magnesium and remove 3 electrons, because that would be first, second and third all together. Each ionization energy only removes 1 electron. Okay, so those will be the sort of equations you'd construct for first, second, third ionization energies, etc. Okay, now then what we do is, after that, we may be given a graph. So let's take an example of a graph that might come your way, and how we might interpret that graph of perhaps successive ionization energies in terms of a question. So if we look at this question here, okay, so we have got an increase in ionization energy as we remove 1, 2, 3, 4 electrons, or 5 electrons, as you might expect. But then we've got this big jump here. So what does that actually mean? How do we use that? How do we interpret that? Okay, well, that means as we go 1, 2, 3, 4, 5, that tells us there are 5 electrons in the outer shell. Because as you might imagine, when you go into the next shell, the amount of energy needed to remove those following electrons increases significantly. So we could actually, if this is all the ionization energies of this substance, we could say we've got 5 electrons in the outer shell, and we have 2 in the inner. So it's got electron arrangement of 2, 5. So in actual fact, there's evidence for presence of shells, but we can also identify that as nitrogen because its atomic number must be 7. Okay. You might also get that perhaps as some values. So if we look at this one here, the first 6 ionization energies of M is this. So we have 1, 2, 3, and then look here, we have a massive jump. So that tells me I have 3 electrons in the outer shell, which tells me that it's in group 3. Now it doesn't give me the identity because it just says that this is the first 6 ionization energies of this substance. It then asks me what's the formula of its oxide. Well, its oxides are 2 minus, group 3s are 3 plus. So if I do my balancing of my charges, I will see that I will need 2 M's to 3 oxygens. So the answer for that must be D. This question here, the first 6 ionization energies of Z are given. Okay, so again, which ion is formed when Z reacts with chlorine? So let's have a look and see if we can establish where the big jump is. So we've got here 590 to 1100, and then we've got a significant jump there to almost up to 5000. The next jump's just up to 6.5, the next jump's up to about 8, and then the next jump's up. So we have a jump here of about 2000, 2000, 2000, and then this jump here is nearly just under 4, just a little bit less than 4000. So there are 2 electrons in the outer shell of this thing, so it must lose 2 electrons and become a 2 plus ion when it reacts with anything. So let's have a look at this question. It asks us to find a group 1 and a group 7 element together. So if we have a look at this graph, at the top, the peak is usually our noble gases. So the one before that, F here, would be group 7. If we backtrack, group 6, group 5, group 4. Some people might think this group 3 is B. They might think that that is actually the group 1. It's not. That's group 3. So that's group 7, noble gas, back down here, okay, to our H. So our H must actually be the group 1. So we are looking for a combination down below here of F and H. So H, group 1 is H, group is F. So the answer there is indeed C. Okay, let's have a look at maybe another couple. Right, so let's have a look at this. Which one of the following lists the first ionization energies for magnesium, aluminium, silicon, phosphorus and sulfur in that order? Right, so how do we do that? Well, we need to refer to where these are on the periodic table. So we have got aluminium, we've got magnesium, we've got silicon, phosphorus and sulfur. So remember our trend from earlier. There's a general trend of increase in increase in first ionization energy, but you also have to remember that magnesium down to aluminium, there was that little blip where we go S to P, then we went up to silicon, then we went up to phosphorus, and then again there was that little blip which would bring us down to sulfur. So we're looking for a trend here where we start and we go start and then we drop straight off. So no, there's one where we go up and we drop and then we go back up again, and then we go back up again, and then we drop back again. So the answer to that must of course be answer C. So that'll be a fairly typical exam question again. Let's have a look at this, and this actually gets the successive ionization energies of boron. So we'll just very quickly check. Boron is here, it has 5. So it would be, so we're after the first 5. So if we just think of boron as 1s2, 2s2, 2p1, or we can in this instance just look at that as 2, 3. So we're looking for first 1, 2, 3 in the outer shell, so they go up kind of steadily, and then the last 2 really we're looking for a bit of a jump, and then okay, so that's what they'll be looking for, 3, 2 and a jump. Okay, plot successive ionization energies of aluminium. So aluminium, if we think is 13, so we're 2, 8, 3. So 1, 2, 3 in the outer shell, Then we have a big jump to 1, 2, 3, 2, 3, 4, 5, 6, 7, 8, and then our last two, another big jump, and then we would join those up, illustrating 3 in the outer shell, 8 there, a bit sloppy, but you get the picture, and then 2 up there. That's not an electron, so it's just 1, 2. Okay. Right, we'll have a look at another couple. So the successive ionization energies of an element are given in kilojoules. Which group does the element belong to? Okay, so let's have a look. Again, we're looking for a big jump somewhere along the line. This is similar to the other one actually. So this goes up by about 500, and then suddenly we have a big jump here by just under 4,000. So 2 electrons in the outer shell. So that is group 2. Successive ionization energies of an element in period 2 are given. We've got to identify that element, so it's in period 2. So let's look for a big jump. Okay, so we've got about 1,000, couple of thousand, and then we have a massive jump up to 37,000 here. So those must be my outer shell electrons. So it must be group 4. We've got to make sure we get the right period. So it's in period 2. So we go to period 2. We go across to group 4. We hope that carbon is a possible answer here, and it is. So therefore carbon is indeed the answer there. Okay, last couple then. Which one of the following lists the first 4 ionization energies of a group 2 element? So again, we're just looking for a big jump from 2 to 3. There, not really. Here, that looks promising. Here, not really. Here, not really. B, big jump. Okay, I have about 6, just over 6,000 there. Okay, so we've gone through most of that stuff, guys. I think we've gone through quite a few of the questions that might come up or be of some use. I'll do this last one, which is sort of a common one where you're asked to work out the formula of something. So we've got the successive ionization energies of X and of Y here, the first 7, and we've got to work out what would the formula be. So we're essentially looking to work out what group is X is in and what group Y is in. So let's go through them and look for a big jump. So, well, there we go. So from 2,700 up to 11,000. So X, I would say, is in group 3. We form 3 plus ions. Let's go look and see where Y, we get our big jump in Y. Okay, so there it is there. Okay, 13,000 up to 71,000. So Y, therefore, is going to be in group 6. Okay, and anything in group 6 is 2 negative. So X and Y, if we balance out our charges, okay, would give us that formula, which is answer C. Okay, hopefully that will help you with your electron configurations and your ionization energy questions.